minimum height trees looks innocent. Until you try every root and blow up to ON squared. Bong interviewers love this because the optimal trick is stunningly simple. Peel the tree from the outside in until 1 to 2 centers remain. Master this, and you'll be ready for graph center/diameter problems on the spot. Let's attack it with basics. We're given n nodes labeled 0, n1 forming a tree, connected, acyclic, and an edge list. We need all node labels that can be roots producing minimum height. A tree's minimum height roots are exactly its centers, 1 or 2. Brute force, run BFS/DFS from each node to compute height ON squared. Instead, observe, if we trim leaves layer by layer, like topological sorting, the last 1 to 2 nodes left are the centers. Why? Because removing leaves doesn't change centers. We're shrinking toward the core. Complexity. ON time and ON space. Handle tiny cases. If n less than or equal to 2, return 0, n1. Build an adjacency list and a degree array. Initialize a queue with all leaves, degree 1. While more than 2 nodes remain, pop current leaves, reduce neighbor degrees, and collect new leaves. Return the last batch of nodes in the queue. They're the centers. Now let's solve solution 1 for the minimum height trees problem. This time, we'll use a technique called topological trim, also known as peeling the leaves. I'll walk you through the idea first, then explain the entire code line by line in simple and clear language. Time complexity is ON, where n is the number of nodes in the tree. We visit every node and every edge only once. The idea of topological trim. A tree center is where the minimum height tree will be rooted. Leaves are nodes with only one connection. If you remove all leaves at once, new leaves will appear. You keep peeling off layers of leaves until only 1 or 2 nodes are left. Those nodes are the centers of the tree. Why 1 or 2 nodes? Because a tree can have 1 center, odd length path, or 2 centers, even length path. Line by line explanation of the code. We import dec, which gives us a fast queue, perfect for processing leaves layer by layer. We define our solution class. This function will return the list of nodes that form minimum height trees. If there are no nodes at all, the answer is just an empty list. So we return an empty result. If there's only 1 node, it's trivially the center of the tree. We return node 0 as the only possible root. We build an adjacency list for the graph. Every node maps to a set of its neighbors. We create a degree list that stores how many connections each node has. We loop through every edge in the tree. We add each node to the other's neighbor list. Trees are undirected, so the connection works both ways. We increase the degree count for both nodes. This helps us identify which nodes are leaves. We gather all nodes with degree 1. These are our initial leaves. Then we place them in a queue so we can peel them off layer by layer. We track how many nodes are still in the tree. We keep peeling leaves until only 1 or 2 nodes remain. Those last nodes are the tree's centers. We count how many leaves there are in this round. We remove all current leaves from the total number of nodes. We process each leaf one by one. We take the next leaf out of the queue. We look at every neighbor connected to this leaf. We wrap it in a list so we can safely modify the graph. We remove the leaf from its neighbor's adjacency list. We decrease the neighbor's degree because it lost 1 connection. If the neighbor becomes a leaf after trimming, we add it to the queue for the next peeling around. When only 1 or 2 nodes remain, these nodes are the tree's centers. We return them as the roots of the minimum height trees. And that's how this algorithm works. It first builds the graph and counts degrees, then repeatedly peels off the outer leaves until only the center remains. Efficient, simple, and elegant. Trees with 1 center produce 1 minimum height tree. Trees with 2 centers produce 2 possible roots. Peeling leaves works because height is minimized at the tree's center. This method is linear, ON, since each node and edge is touched only once. Now that we've implemented our solution to find the minimum height trees, it's time to test it with an actual input. This helps us see how the algorithm trims leaves from the tree level by level to identify the root nodes that produce the minimum height. We'll walk through the input, observe how the leaves are removed, and confirm that the output matches the expected result. Let's test the function using this input. We have n equals 4, representing 4 nodes labeled from 0 to 3, and an edges array defining the connections between them. This tree structure forms a star centered at node 1, which connects to nodes 0, 2, and 3. Here's why the solution works. The algorithm builds a graph and counts the degree of each node. It then identifies the initial leaves, which are nodes with only one connection. One layer at a time, it removes these leaves and updates the degrees of their neighbors. This process continues until at most 2 nodes remain. Those remaining nodes are the roots of the minimum height trees. For this example, the initial leaves are 0, 2, and 3. After trimming them, only node 1 remains, which is the root of the minimum height tree. And that is exactly what the program outputs. 1. This verifies that the code works correctly and passes this test case. So our implementation is correct. The algorithm successfully identifies the center nodes that minimize the height of the tree. It handles the given structure accurately and returns the expected output. The BFS-style trimming ensures efficiency and guarantees that the minimal height roots are found. Now let's solve solution 2, finding the minimum height trees by identifying the middle of the tree diameter. We'll use BFS to find the farthest nodes, reconstruct the diameter path, and pick the middle nodes as optimal roots. Time complexity is O(n), where n is the number of nodes in the tree. BFS is performed twice, and path reconstruction is linear. We import deck to efficiently perform BFSQ operations. We define a class solution to hold our method. The function findMinHeightTrees returns the roots of minimum height trees given n nodes and edges. If there are only 1 or 2 nodes, all nodes are MHT roots. Build an adjacency list for the tree. Each node stores its neighbors. Define a helper BFS function that tracks visited nodes, uses a queue, keeps the farthest node, and remembers parents for path reconstruction. Perform BFS for each node, explore neighbors, mark them visited, record the parent, and update the farthest node. Return the farthest node in parent dictionary. Start BFS from node 0 to find one endpoint of the diameter. Perform BFS again from that node to find the other endpoint and record parent pointers for path reconstruction. Reconstruct the path from node A back to Nadia using parent pointers. This path is the tree diameter. Return the middle nodes of the path. If the length is odd, return 1 node. If even, return 2 nodes. These are the minimum height tree roots. BFS is performed twice. Reconstructing the path takes O(n) time. The middle nodes ensure minimum height for the tree. Before checking the output, let's understand the problem. We are given n equals 6 nodes, edges equals 3, 0, 3, 1, 3, 2, 3, 4, 5, 4. The goal is to find all roots of minimum height trees, nodes that produce the smallest height when chosen as tree roots. Let's test our function with this input. Here, we have a tree with 6 nodes, connected as described by the edges. Here's why the solution works. Build the graph. Represent nodes as adjacency lists. Use BFS to find tree diameter. First BFS from any node. Here, node 0 finds one endpoint of the diameter, Nadia. Second BFS from Nadia finds the other endpoint, nodeb, and keeps track of parent pointers to reconstruct the path. Identify middle nodes. The diameter path is the longest path in the tree. Nodes in the middle of this path are the roots of MHTs. If the path length is even, there are 2 middle nodes. If odd, 1 middle node. Step by step with this input. BFS from 0 farthest node is 5, BFS from 5 farthest node is 3, diameter path, 5, 4, 3, 0, or similar middle nodes, 3, 4. These nodes will produce minimum tree height when chosen as roots. And that is exactly what the program outputs, 3, 4. This confirms our code works correctly for this test case. So, our implementation is correct. It successfully identifies MHT roots, efficient, accurate, and reliable. Our implementation is correct. It accurately finds the diameter of the tree. It correctly identifies middle nodes as MHTs. Let's wrap up the minimum height trees problem. At first, it seems like you just need to pick the best root, but trying every node quickly explodes into O(n)². The clever trick here? We don't search from the roots outward, we peel the tree inward. Breakdown recap. We're given n nodes forming a connected, acyclic graph, a tree. Our goal is to find all possible root nodes that produce the minimum height when the tree is rooted there. In simple terms, we're looking for the tree's centers, the points that minimize the longest path to any leaf. Assess recap. The brute force approach would be to run BFS or DFS from every node to measure height, but that's too slow. Instead, we realized that the tree's centers can be found by trimming leaves layer by layer, just like peeling an onion. Each round, we remove the outermost leaves until only 1 or 2 nodes remain, which are the centers of the tree. Structure recap. We handled small cases first. If there are 2 or fewer nodes, we just return all of them. Then we built an adjacency list and tracked the degree of each node. Next, we added all current leaves to a queue, and while more than 2 nodes remained, we kept removing those leaves, updating their neighbors, and collecting new ones as they appeared. The final remaining nodes are our centers. Implement recap. After coding this peeling logic, we ran it on LeetCode, and the solution executed smoothly without any errors. Check recap. We verified it across multiple test cases, and each time, the output correctly identified the minimum height tree roots. Closing insight. The big lesson? Sometimes, finding the center of a problem means working from the outside in. By trimming layer by layer, we let the structure reveal its own core, efficiently, cleanly, and in linear time.